Hi, this is Mrs. Young, and today's lesson, our fourth lesson on our circle unit, is all about inscribed angles. We're going to have three theorems and a corollary and a few definitions here. So no bell ringer, we're going to just go ahead and jump in and write down our vocabulary terms. We have inscribed angle, intercepted arc, and subtends. And these are all terms I'm going to be using throughout the lesson today. So why don't you pause the video and go ahead and give yourself a minute to copy down these three vocab terms, and then I'll come back and talk about them. So an inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So like in my picture, my example here, angle DEF is an inscribed angle because its vertex E is on the circle, and then its sides are chords of the circle, right? So DEF is considered an inscribed angle. Intercepted arc, it's an arc whose endpoints lie on the sides of an inscribed angle and all the points in between them. So DF, that arc DF, is called an intercepted arc. We say that that arc DF subtends that inscribed angle because it's the arc across from that angle. Right? So we've got inscribed angle. This is different than most often, or right before this, we were talking about central angles, right? A central angle is an angle whose vertex is on the center of a circle, central angle, center of the circle. An inscribed angle has its vertex on the circle. So those are three important terms that we need to know going through today's lesson. So our first theorem is called the inscribed angle theorem. The measure of an inscribed angle is half the measure of its intercepted arc. So in each of these examples here, we have three different cases, 1, 2, and 3. The angle ABC is an inscribed angle. And that angle is always going to be half of the arc that it's across from. This is different than our central angles. In a central angle, I'm just going to try to draw one in here, right? This would be the central angle across from this arc, and that central angle would be the same measure as that arc, right? So that like arc AC here looks like it's 90 degrees, and that central angle looks like it would be 90 degrees as well, but you can tell that the inscribed angle of that same arc that's definitely not 90 degrees, right? It's actually half of that. So that inscribed angle is half of the arc that it's across from. So this is really an important theorem. Go ahead and pause it and copy this down. So here's just a quick example of our inscribed angle theorem. This is also in the packet that's posted in Google Classroom. It's one of the check it outs in today's lesson. It says find the measure of arc ADC. So if you look at this picture over here, if I go from A to D to C, which is all the way down here, right? If I go from A to D all the way over to C, right? I've got that huge arc, and we want to find the measure of that arc. But I can see that there is an angle inscribed in that arc, right? This angle ABC is inscribed in this arc. We would say that arc ADC subtends that angle. So we know that the arc is twice as big as the inscribed angle. So if I take 135 and I double it, I get 270. The measure of angle DAE, if I look right here, DAE, that's an inscribed angle, and this angle is an inscribed angle across from this arc that's 76. So if I take 76 and cut it in half, I think I get 38. Yep, 38. So there's two quick applications of that theorem. We have a corollary that follows directly from this theorem. It says, if inscribed angles of a circle intercept the same arc or are subtended by the same chord or arc, then the angles are congruent. You can see in this picture they kind of color-coded their angles. They have angle ACB, they have angle ADB, and then finally they have angle AEB. So the red, the blue, and the green angles are all inscribed angles across from this same arc AB. So those angles must all be congruent. Conversely, if you look at it from the other side, they're showing you the reason they're saying this is that angle CAE and CBE, these are both across from this same arc, so those angles would also be congruent. It kind of makes sense. That's why it's a corollary. It just follows directly from the theorem. The only thing that concerns me is sometimes when the pictures get a little confusing, it's not always going to be color coded like that. So it's going to get a little tricky when there's a bunch of lines drawn inside a circle like that. So again, there's our corollary. Another, check it out from our packet. Just a couple quick practice problems. It says find the measure of angle ABD. So if we look at our picture, here's angle ABD, and it's across from this arc that's 86. So if I take 86 and cut it in half, I would just get 43. Notice also, okay, there's angle ABD, but then also angle ACD is an inscribed angle across from that same arc. So that angle would also be 43 degrees. Just pointing that out. And then here it says to find the measure of arc BC. Here's arc BC. It's across from, right, this inscribed angle that's 60. So if I take 60 and double it, I get 120. So remember that the arc is twice as big as the inscribed angle, or the inscribed angle is half as big as the arc. Kind of goes back and forth. Okay, on to our second theorem for today. This is an inscribed angle subtends a semicircle if and only if the angle is a right angle. Remember, if and only if means it's a biconditional statement, that the conditional and the converse are both true. So if an inscribed angle subtends a semicircle, then it's a right angle. Or the converse, if an angle is a right angle, then the inscribed angle subtends a semicircle. We know that all the way around a circle is 360. We know if we have a diameter, it's going to cut that in half, right? So half of 360 would be 180. So we know that the angle inscribed across from that arc would be half of 180, so it would have to be 90. So that's why that has to be a right angle or 90-degree angle. I would encourage you to pause the video here and go ahead and copy down this theorem. So another couple of quick examples. Again, this check it out is in your packet for the lesson for today. In the first one on the left side, it says find Z. I can see that this angle ABC is inscribed. Here's a diameter, so I know that that's half the circle. So half of 180 would be 90. So I know that that angle B, 8Z minus 6, must equal 90. And then we can just go ahead and use algebra to solve this. 96 divided by 8, I'm going to come up with, I believe, 12 for Z. Let me just double check my answer. Yes, they might even take this a step further. They might ask us to find the measure of that angle, but we know that it would be 90. So a quick double check, if you plug that in, we should get 90 if we plug it back in. In the next one, in 3B, it says find the measure of angle EDF. If we look at this picture, angle EDF is right here, right? It's 2x plus 3. I noticed that that inscribed angle is across from this arc, but I also noticed that angle EGF is also an inscribed angle across from that same arc. So this is from that corollary we talked about. Those two angles must be the same measure. So we can use that to set up an equation. 2x plus 3 equals 75 minus 2x. And then we can go ahead and use algebra to try to solve this equation. See if I can do this. So it looks like I get x is 18, but notice that in the problem it said to find the measure of angle EDF, right? That's this angle right here. So 2 times 18 plus 3, so 36 plus 3 is 39. A way that I could double check this is I could plug in 18 into the other expression and see if I get the same value, right? I should if I'm doing it correctly. So if I plugged in 2 times 18 over here, I'd get 36, and 75 minus 36 is also 39. So just another way that I could double check my answer. And then we have another final theorem here. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So if we look at this picture, we have a quadrilateral, ABCD, inscribed in a circle. What does that mean? That means that each of the vertices of our quadrilateral lie on the circle. So that's a quadrilateral inscribed in a circle. When they talk about opposite angles, as an example, if I look at angles A and C, you can see that angle A is across from this arc here, right? And we can see that angle C is across from this arc here. And if I put those two arcs together, I'm going to get a whole circle. So 360 cut in half would be 180, because we know the inscribed angles are half of the arc. So I know that those two angles A and C would have to add up to 180. That's where that supplementary comes in from. So we know that angle A plus angle C is equal to 180. Same thing with angles B and D. So I want you to pause the video and go ahead and take a minute to copy down this theorem. And then we have just a quick example with that theorem. Again, this check it out 4 is in your packet as well. It says find the angle measures of JKLM. So I can see that this quadrilateral JKLM is inscribed in this circle. I'm given expressions for K and for M, and those angles are across from each other. So we know they're going to be supplementary or add up to 180. So we can say 4x minus 13 plus 33 plus 6x is equal to 180. And then we can go ahead and use algebra to solve this equation. Hopefully I'm doing this right. So I got x is 16. Let me just double check. But notice that it says find the angle measures, right? They want us to find all the angles. Well, for angle K, you're just going to plug in 16 here. For angle M, you can plug in 16 here. Now I can use this expression and plug in 16 here to solve for angle L. But then how can I figure out the measure of angle J? You should remember that the 4 angles of a quadrilateral add up to 360. So then you can take 360 minus those 3 angles to see what's left over or remaining for angle J. So you should come up with 108, 129, 72, and 51. Again, just double check these 4 values do add up to 180. Notice how, ooh, actually I put this out of order. J should be solved last, right? I would solve for all the other ones and then use that to solve for that angle J. Finally, just a couple of quick practice problems for you. So there's just 3 here. Solving for different angle measures. I would like you to pause the video and go ahead and solve for each of these. So in the first one, angle RUS, that's my green angle right there. It's across from the arc that's 50, so half of 50 is 25, super easy. In number 2, we're solving for A. This angle is across from this arc. So I set that equal to 90 because I can tell that RU is a diameter. It goes through the center. So I know that angle equals 90. So I solved that equation for A and got A is 3. And then finally, in number 3, this is similar to the last theorem that we looked at. It says find the angle measures. So again, these opposite angles are supplementary. They add to 180. So I get y is 18. And for the other opposite angles, I get x is 4. Using those values, I can plug them back in and solve for each of the different angle measures. It's kind of unique in this problem that you got, technically, I guess this quadrilateral winds up being an isosceles trapezoid because its base angles are congruent, right? So that's just kind of unique to this problem. It doesn't always happen like that. So again, you should have been able to solve for x and y and then solve for each angle measure. Your homework for tonight is on the stamp sheet that's posted in Google Classroom, but I'll go ahead and write it down here for you. So it's going to be page 23 and 24, numbers 12 through 27. 12 through 27. Again, make sure you're drawing your pictures and showing your work. Okay, thanks guys. See you later.